Okay, guys, continuation on the refrigeration cycle. So we stopped at the properties of refrigerant last time, so we continue on this lecture from here. So what are the key properties of refrigerant? So the first of them is the latent heat of vaporization. So the refrigerant at a high latent heat of vaporization is preferred. So for a given capacity, a high value of latent heat of vaporization indicates that a smaller amount of refrigerant will be circulated and required per unit time. So if the property of the refrigerant has a very high latent heat of vaporization, then that could account for a smaller amount of refrigerant being used in the system. Then what about the condensation pressure? So excessively high condensation pressure requires considerable expenditure on heavy construction of condenser and piping. So therefore, we need a refrigerant with a better compression compression pressure quality. Okay. So what about the freezing temperature? The freezing temperature of a refrigerant should be below the evaporation temperature. And the critical temperature, the refrigerant should have sufficiently high critical temperature. As a temperature above the critical temperature, the refrigerant vapor cannot be liquefied. So when using air-cooled condensers, the critical temperature should be above the highest ambient temperature expected. Okay. The toxicity, a refrigerant obviously should be non-toxic because it helps with minimizing the level of toxic materials in circulation in terms of food handling, and in any case it gets released in the environment, it should be a material that is non-toxic, as it could cause harm and issues to people in contact with or animal. Corrosiveness, the refrigerant should not be corrosive material because the material used in the construction of the refrigeration system should be, if the refrigerant is corrosive, then they wouldn't last long. So the materials for the evaporators, the materials for the condensers, and even the compressors will be affected if the refrigerant which flows through these materials is corrosive. What about flammability? The refrigerant should be non-flammable, so it should be a compound or chemical that is non-flammable. Okay. Chemical stability should be a chemical that is not reacting, inert chemical, or a chemical that will take lots of work to get it to react. So a chemical that is a compound that is chemically stable, okay, will be preferred. So if a leak develops in the refrigeration system, the detection of such a leak should be easy. So a refrigerant that makes detection very easy is preferred to the one that doesn't. Okay. So what about the cost of refrigerant? Obviously, in industrial application, a low-cost refrigerant is preferred. And environmental impact, we touched on it on the toxicity as well. It should be although in known history, most of the refrigerant have compounds that could harm the environment, but there are some refrigerants which have a better performance with respect to the causing harm to the environment, okay, due to their properties. So this is a standard designation given to some of the common refrigerants used in the market. And we have the halocarbons. The halocarbons are the halides from the periodic table, and they are all made up of chlorine, fluorine, and we know the chlorofluoro effect on the environment. Okay, so the halocarbons are listed with refrigerant number of R12, R22, R30, R114, R134A. So these are the corresponding chemical names and the formula for this refrigerant. Then the azeotrops are given as the R502, and these the chemical names are the R22/R115, and the chemical formula is given as this. The inorganic compounds, which is the R717, is mainly ammonia. Okay, and the chemical formula for ammonia is given as this. So this is a typical comparison between commonly used refrigerants based on their performance on if minus 15 degrees Celsius evaporator temperature and a 30 degrees Celsius condenser temperature. Now you can cross-check both their molecular weight, the boiling point, and if you look clearly, the lowest boiling point is from the Freon. Okay, is from Freon 12. That is R12 has the lowest boiling point. Condensing pressure at 30 bar. It has a lowest condensing pressure. What else? So with this you can judge. None of them is flammable apart from ammonia. Ammonia is the most flammable one. Okay, and it has an acrid odor. So if you are to detect leak, you can use the odor to identify which if there is a leak in the system. Okay, so these details will actually give you information on the suitable uh, level of refrigeration that you want, and this can help you to select the refrigerant suitable for your refrigeration process. Okay. So other thermodynamics properties, in this case for a refrigerant 134A, is given here as well. So the pressure enthalpy chart, as we've already established from the previous lecture, we have the bell curve, the solid black line with a bell shape. Then on this side, we have the subcooled region, where on the bell curve here, the saturated liquid refrigerant flows, and after the critical point, the saturated vapor refrigerant exists here. Then the space after this saturated vapor line becomes the superheated region. We have the constant temperature line, which goes into the constant pressure line as well, and also constant temperature line, and the line goes downward. Then from the bell curve on the right hand side, which denotes the saturated vapor line for the refrigerant, there is an increase, okay, a curve that shows a compression process line increase, which shows a constant entropy curve and a constant and a superheated compression for the saturated uh, vapor refrigerant here. Okay, so the lines pointing downwards from here to here shows the expansion process, and the line pointing horizontally to the right hand side shows the evaporation process. So the evaporation process moves from saturated liquid to saturated vapor. Okay, and the uh, x-axis here gives us the values of the enthalpy at any point within the chart here, and the y-axis gives us the pressure reading at any point within the chart here. Now the lines covering the regions under the bell curve gives us the dryness fraction, which is the quality of the refrigerant that falls between the saturated liquid line curve and the saturated vapor line. Okay, so this bell curve exists for different refrigerants. So for a refrigerant R12, we have a known curve with the values produced uh, experimentally for the enthalpy and pressure relation with the values of the temperature. Okay, as we can see, constant temperature value is written at the end here. So if we blow it up to show a little bit more clearer, using the pressure enthalpy chart for a refrigerant R134A, we can see clearly the temperature line for a 20 degrees Celsius. The constant temperature line meets the constant pressure line here, and it continues and falls that way. Okay, and we can see the solid saturated liquid refrigerant liquid line here until the critical point, and from here we can see the saturated vapor line. Now this red line going up here gives us the superheated. So we know that this region is superheated region and this region is subcooled region. So these lines going up here shows us the detail for the superheated uh, section. Okay, so what else do we have here? And the enthalpy readings for each of these is denoted by a solid blue lines here. Now under this bell curve you will see a thin blue lines showing percentages. So this is the percentage for the dryness fraction, the quality of the refrigerant mixture. So the liquid vapor mixture of refrigerant that falls between the bell curve, okay, between the area underneath the bell curve. So the pressure enthalpy chart may be divided into different regions based on the saturated liquid and the saturated vapor curve. Okay, so in the sketch shown, the area enclosed by the bell shape here, okay, so it shows the area represented by the two-phase region of both liquid and vapor. That shows you the percentages, as we can see here, of the which denotes the dryness fraction. Okay, so the horizontal lines extending across the uh, chart shows you the pressure. So the thin blue line extending across shows you the pressure. Okay, the thin blue lines, and the pressure reading here is 1 megapascals, corresponding to 1 megapascals here, and the thin line going upward vertically shows you the enthalpy. Okay, the red line that goes to this way and that way shows you the constant temperature lines. Okay, so the area on the left hand side is known as the subcooled region, where the liquid refrigerant with temperatures below the saturation temperature for the corresponding pressure. And the area on the right is a saturated vapor, is right of the saturated vapor line is known as the superheated region. So at the superheated temperatures above the saturated temperature of the vapor at constant pressure. So within the bell-shaped curve, we have the dryness fraction, as we've already established. So, and this is how the full chart will look for a refrigerant R134A. Okay. So since the superheated region is crowded with a number of curves, an expanded portion for that region is more convenient to use to draw process 1 and 2. Okay. So that expanded process could be plotted. So you can plot from this is superheated line, okay, the superheated section. So processes 1 and 2, which is a compression process. So if the evaporation starts from stage 4 and ends at some point here on the saturated vapor line, then you can plot a straight line, or you can choose one of the lines. Let's see, this line meets so let's say the evaporation process stops at -10. Now if we follow this line here to a certain constant pressure, maybe in this case a pressure of 1 bar, okay, we stop here at no 10 bar here, and 10 bar and 40 degrees Celsius, then we followed from this line to here. So the new superheated point, which is the position here at 2, we trace downwards to give you a new enthalpy for that. Okay, we will get into this more details with examples. Okay, so this is a chart for ammonia, and this is how it will look. And as you can see, the chart for R134A looks the superheated lines looks a lot more steep compared to the ammonia, the R717. Okay, it looks a little more, it's not as steep as the previous chart. So there are different charts for different refrigerants. So when in case of calculation or assignment or exam, any particular refrigerant which is given to you, the corresponding tables and the chart will be given to you as well for your calculations. Okay, so we can read out the details for these stages, which is the stages 1 to 4 from the chart, or we can also make this, there are tables just like the steam tables presented for these properties, for enthalpy, for entropy, density, absolute pressure and temperature for this refrigerant. So we can also read out the values from the table, but it's always advisable to sketch it out on the chart, because usually it's very easy to find the compression side of the compression side and the figures from the compression side with the chart. Okay, so another approach to determine the thermodynamic properties of refrigerant is to compute computer-aided methods with empirical correlations. And for more details of this subject, you can consult this textbook to extract the information for the computer-aided empirical correlations. Okay, so example. So a cold storage room is being maintained at 2 degrees Celsius. It's being maintained at 2 degrees Celsius using a vapor compression refrigeration system that uses Freon R134A. Okay, the refrigerant is R134A. So the evaporator and the condenser operates at -5 and 40 degrees Celsius. So -5, which is the low temperature here, and 40 degrees Celsius, which is the high temperature here for the condenser and evaporator. So evaporator -5, condenser 40 degrees. So the refrigeration load is 20 tons. Calculate the mass flow rate of refrigerant, the compressor power requirement, and the coefficient of performance. Assume that the unit operates under saturated conditions and the compressor efficiency is 85%. So using the table for the refrigerant R134A, so we can plot with the known temperatures for the evaporator and condenser, we can plot this cycle on that chart. So plotting this cycle on that chart, so we go for a temperature of -5. What is the equivalent temperature of -5? So if you look here, this is -10, and if you look here, this is 0 degrees. So the distance between -5 and 0 degrees, -5 and this is not clear, but the distance between -10 and 0 degrees here is 5 degrees, -5. So we draw a line from here, draw a line straight. Okay, that's the easiest way to do it. Draw a line straight. Now we go to 40 degrees. So this is 20. So this is 10, 20. So this is 0, 10, 20, 30, 40 degrees. So the condenser operates at 40 degrees. So we draw another line for 40 degrees, a straight line. Okay. Now, because we are here, we have to draw another line to show the compression side of things. And once we are able to draw these two lines, then we draw a straight line from the top here to the bottom. So we can delete the line here, delete that line here, and this gives us this section sorted. But what about the superheated the compression side of things? So from this point here, you can draw a straight line in between the existing solid lines. So depending on which side of this point you stop, make sure that the line you draw, in this case this red line here, do not intersect with any of the solid lines here. So meaning that any point in between these two solid lines, okay, we do. And once you get to that, once you meet the condenser line at the top, then you can draw another line to read out the corresponding enthalpy. So with this, we have been able to identify our H1, H2, and H3 with ease. Okay. So there are other ways to do this. If we are able to use, if we can use the tables as well. Okay, you can achieve the same thing by using tables. But for now, using this chart is pretty straightforward. Okay, so with that, we can read out the values for the enthalpies. So at stage stage 1, we can read out the enthalpy value, which is between 280 and 300. Okay, so this gives us 296 kilojoule per kilogram. And we go to the superheated at stage 2, which is H2. We can read out between 320, 330, so somewhere 327 or 327. Then saturated liquid when temperature is 40 degrees, that is H3. So we read out H3 here. So from 40 degrees, we go down to this point, and this is 140, 150, 160, so almost 160. So we go down, we take 160 and a clear approximation, and we know that H3 and H4 is the same. So H3, H4 is equal to same. Now we know that at stage 1, we have a saturated vapor, and at stage 2, we have a superheated vapor. At stage 3, we have a saturated liquid, but at stage 4, we have a liquid vapor mixture. Okay, saturated liquid vapor mixture. So since we have arrived at this, we can find the total heat in. So the total heat in is between these two places, the change in enthalpy between H1 and H3, or H4, because they are the same, and that gives you the total heat added. Then the work done by the compressor between points 2 and 3, and that gives us the change in enthalpy, and we arrive at minus 31. So the heat out of the condenser, which happens between stages 2 and 3, okay, is giving us H3 minus H2, and we have minus 167 kilojoule per kilogram. Then the refrigerant flow rate, we know that the total heat in is the heat load as we given in the question. It says that the refrigeration load is 20 tons. So if we know the refrigeration load as 20 tons, then we multiply it by the ton for one ton of refrigeration, and it gives us the total power for refrigeration. And if we know the total power for refrigeration, and we know the total heat added per kilogram, and we can use that particular equation to find the mass flow rate of refrigerant. And the mass flow rate of refrigerant is 0.517. What about the compressor power requirement? So the power requirement for compressor, as we know, is the work in divided by the efficiency of the compressor. And in this case, we are given the efficiency of compressor, which is in micron, as 0.85, and if we divide that by the work done by the compressor, then the work requirement is 18.86 kilowatt. Now, the coefficient of performance, which is the heat in divided by the network, then the network is done between 1 and 2, and if we use that, we can divide the total heat added to the system, and that will give us a coefficient of performance that is 4.387. Okay, so example 3. So the example 3, instead of using the chart for that particular refrigerant R134A, we can repeat this calculation using the thermodynamics table for the Freon R134A. So if we do so, from the table reading, and in this case, we have R134A. R134A. Like, as you know, I will attach another table. I will attach these tables in the lecture material section in Moodle so that you have access to the different refrigerants and the tables. So we are looking for R134A. So this is R134A. So we have what are the questions? So we have at -5 degrees Celsius. So the corresponding H1, which is Hg, then that would be 295.59. So on the R13A, so -5, where is it? -5. So this is the enthalpy of the vapor. So if we trace it down to, okay, see -1, -5, we go to enthalpy and it gives us 295.588, which we have here 295.59. Then the superheated section, we get the superheated section from the graph. So this is the importance of the graph. Okay, we always use the chart, the graph chart, for the superheated section. But for the saturated vapor and saturated line, we can get that from the, you can also get this from the graph if you want, but you can go to the table to get this as well. So 40 degrees Celsius, and you can go to this table under 40 degrees Celsius, then you can read out the corresponding figure for the saturated liquid line. So if you go here, 40 degrees, the figure for the liquid section, which is something here, for the liquid, which is here, 40 degrees, 156.5, something like that. So yeah, so this now is equivalent. Where is H3? H3 is the same as H4. Okay, so you can carry on with this. Okay, so you do similar thing we've done before to calculate the total heat added to the system, to the evaporator, and we do the same for the compressor. And you see that the values, the figures are very, very identical to each other. Then you do the condenser heat removed from the condenser, and we do the heat load. Okay, and with the heat load, you can calculate the flow rate of the refrigerant, and you can see that the figures that we arrive here are just similar to the figures that we arrived using the chart. Although there are minor changes, but the changes are not uh, much. Okay, so we do the same for the work requirement for the power requirement for the compressor, and we do the coefficient of performance, and we arrive at similar values. Okay, so these are the two ways we can use to do this calculation for the refrigeration cycle, for the ideal vapor compression cycle. Okay, so with this, you now know how to do to use the charts to do the calculations, and also how to use the table. So I will implore you to attempt the tutorials This is similar to what we've been doing before using the steam table and things like that. But this one is a lot more easier because you can easily get the figures and plug it in the calculations and on you go. So with that said, we can move on to the multi-stage system. So what are the multi-stage systems? These are the systems that involve using more than one compressor, often with an objective of reducing the total power requirement. Although adding additional compressors require an increase in capital spending, the total operating cost must be reduced for the multi-stage system to be adjustable. So a commonly used approach for using a dual-stage refrigeration system is a flash gas removal system. Okay, and in this case, you have the flash gas removal system in order to improve the refrigeration system. So as shown previously, a refrigerant leaves the condenser in a saturated liquid state, and in an expansion valve, there is a pressure drop from a condenser. Expansion valve here, there's a pressure drop from the condenser pressure to the evaporator pressure. Okay, so the drop in pressure of the refrigerant with a partial conversion to a vapor state, commonly called flashing, is accompanied by a conversion of some of the refrigerant from liquid to vapor phase at this stage before it goes into the evaporator. So at some intermediate pressure between P1 and P2, the refrigerant is existing partially as a vapor but mostly as a liquid. The refrigerant already converts the vapor in the expansion valve and uh, and, and can no longer provide the useful purpose in the evaporator. So to increase efficiency, a flash tank, okay, a flash tank here can be used to separate the vapor from the liquid while the pressure drop occurs. Okay, so then we can then take the vapor and compress it with another small secondary compressor here to the condensing pressure. So we can bypass taking that vapor from the flash tank, bypass these processes and to the second compressor and push it back into the line. Okay. So the liquid refrigerant with only a small fraction of the vapor due to the further flashing that occurs is then conveyed to the evaporator, and the evaporator, leaving the evaporator, goes into the primary compressor. So the use of a flash gas system results in an overall decrease in power requirement, and the reduction in power requirements becomes significant when the temperature difference between the condenser and the evaporator is large. So this system is most useful for low temperature chilling or freezing applications. So the secondary compressor required for compressing the flash gas is usually small, and the primary compressor is usually also smaller than in a standard system that does not remove flash gas. So since most of the flash gas is removed, the gas has significantly larger volume than liquid. The piping used for intake and exit of the refrigerant from the evaporator can be smaller. So the additional cost of the flash gas system include the need for a secondary compressor, although small, flash gas tank and associated valve piping and fittings. So this is the end of the refrigeration cycle, and by now you should have all you need for the calculations. And I will also advise and implore you to uh, for personal reading, to go further, make use of the textbook to see if you can attempt to generate the values using the computational method with the figures and the equations that may be provided to you in the textbook. So I will see you guys in the tutorial session. Bye for now.